looking at chapter 7a. This is just the first part of chapter 7. We did the second part last week or the week prior. So looking at this first part, we're going to talk a little bit about nutrition, and then we're also going to talk about some transport mechanisms with bacteria. So first off, looking at nutrition, nutrition is a process where these organisms are utilizing nutrients from their environment, and they're going to use these nutrients to undergo a number of different types of chemical reactions. All of these metabolic reactions, they need these nutrients in order to successfully complete them. Any nutrient that is deemed essential, that is one that must be provided to that organism in its diet. Okay, so that's what we refer to with an essential nutrient. Up here, we can take these essential nutrients and we can split them into macronutrients and micronutrients. Macro versus micro. Macro, think large, micro, think small. Macronutrients they need in large doses, micronutrients they need in smaller doses, smaller amounts. You can think of them as trace elements right here. So looking at this, the 6 most crucial essential nutrients for these organisms are these 6 in this image right here at the bottom of the screen. So schnapps, just going to say that term over and over, it's an easy way to remember it. So with schnapps, we can see definitely carbon, hydrogen, nitrogen. This is actually basically the order of importance with these microorganisms. Okay, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So looking up here, okay, so macronutrients, they're needed in large amounts. Carbon, hydrogen, oxygen, nitrogen is a big one too. You need nitrogen to build proteins. If you think about carbohydrates, like glucose, C6H12O6. You need carbon, hydrogen, oxygen for carbohydrates. Same thing with lipids. Okay, and you're going to see the nitrogen, playing a role with these proteins. So these macronutrients, large doses, because they're going to build these macromolecules, carbohydrates, lipids, proteins, definitely necessary. Micronutrients, they just kind of assist with some, structural aspects of proteins and with the enzymes, helping to turn them on and so on, like cofactors. So we saw like iron or magnesium or zinc acting as these cofactors. So smaller doses for those. All right, so if we were to look at molecules, we have organic molecules, we have inorganic molecules. What is the difference?
One has carbon and the other doesn't.
Very close. Okay, it's a very common answer that one has carbon and the other one doesn't. Inorganic molecules can have carbon too. It's just a little bit different. Can anyone kind of tweak that definition a little?
Carbon chain.
Carbon chain, yes. Carbon chain is the key with organic molecules. With organic molecules, not only a carbon chain, but having at least a carbon to another carbon or carbon to a hydrogen. One of those two absolutely needs to be present in order for the molecule to be organic. You can have methane, okay, which is CH4. So you have a carbon connected to 4 hydrogens like so. That is actually an organic molecule. Even though you don't see multiple carbons. Obviously, glucose would be organic, so C6H12O6, that's going to be organic. You do see that carbon chain, number of hydrogens off of that. Propane, C3H8, that's going to be organic as well. What about if we were to look at something like CO2? We do have a carbon, we don't have another carbon, nor do we have any hydrogens. This is inorganic. What about carbonate? CO3, and it has a 2- charge. Carbonate, same thing, that would be inorganic as well. So organic, you're looking at carbon-carbon or carbon-hydrogen bond. Those are your requirements for organic. Inorganic, you don't have that. So you could say inorganic, you can say hydrogen gas, you could say water, okay, oxygen gas, that's all inorganic. Sulfate, hydrogen sulfide, what we saw with the fermentation flasks. Okay, so that's the difference between the two. What I'd like you to remember in this next little section, it's going to be probably the most confusing topic of the day, is what we're gonna hit in the next 10 minutes or so. When we talk about an inorganic form of carbon, I want you guys to remember carbon dioxide. So if I say an organism requires an inorganic form of carbon, it's just like saying that organism requires carbon dioxide. This is the inorganic form of carbon that we are going to be referencing for the next little bit. Okay, so CO2 is our inorganic form of carbon. Inorganic form of carbon. All right, so carrying on. So we got that covered, so we see the difference between the two. Here we can see different inorganic reservoirs of elements for these organisms. So everything up here is inorganic. Again, carbon dioxide, carbonate, hydrogen gas, water, sulfate, hydrogen sulfide, potassium chloride. Okay, these are all going to be inorganic. Now it's important to take a look at organisms. And I'm not the biggest fan of flashcards. It's not always the best way to study, because a lot of times it's just kind of memorization and then it's gone, right? With this section though, I think it would help you guys to kind of keep things organized. Okay, so I think flashcards, I actually would say I do recommend them for this little section, because it's going to be very confusing, all of this terminology. I mean, this class is like learning another language, and it's going to be very evident with this next little section. So bottom line, here's what we're going to talk about. These organisms, we can categorize them two ways. One way, based on their carbon source, what they need for carbon. Second way, energy source, what they need for energy. Depending on their carbon requirements, depending on their energy requirements, we are going to assign them a name. They'll be in a specific group. Okay. So up here, we categorized based on carbon source alone. So up here you can see there are two categories, heterotrophs and autotrophs, based on carbon source. The term troph means feeding, food, okay? So this is gonna be their, requirement for carbon, so their source of carbon. We have hetero versus auto. Hetero means other, so they're going to primarily require, feed off of other organisms for their carbon source. Heterotrophs, their carbon source is organic. They need an organic form of carbon. That means carbohydrates, fats, proteins. That is all organic. Okay, sugars, proteins, lipids. Okay, so definitely organic. Carbons, hydrogens, all tossed in there. Depending on other life forms, for us, we are definitely in this category of heterotrophs. Okay, our carbon, we can't do anything with carbon dioxide. We need an organic form of carbon. If we were to look at these organisms, the autotrophs, auto means self. You can think about them as self-feeders. What they do is they take the inorganic form of carbon, which we know is CO2, and they make an organic form from it. They convert something inorganic to something organic. We don't do that. Okay, we require organic forms of carbon for our nutrition, but autotrophs, they're going to utilize CO2 in the environment and then produce something organic from it. So what I would like to do right now is I'm going to raise the screen and write out a couple of things up here for you. So first I want to review a reaction we talked about last weak. And this reaction, we have C6H12O6 plus 6 moles of oxygen is going to give us 6 moles of carbon dioxide, 6 water. What is the name of this reaction up here? Glucose and water, and then yielding carbon dioxide. Oh, sorry, glucose and oxygen yielding carbon dioxide and water.
Dehydration.
What's the name of this? Remember we talked about fermentation, anaerobic respiration, aerobic respiration. It uses oxygen. Which of those three would most appropriately fit? Aerobic respiration. This is aerobic. Okay, so here we're looking at a reaction that heterotrophs are going to undergo. Now, we had this on the board last week. I took the time to write it on the board this week. It's probably something good to know for your exam next week. Just kind of tossing that out there. What else did we have as a product from aerobic respiration?
ATP.
Yes, ATP. Because remember, we had this huge, super large glucose molecule. We stripped it down, breaking those bonds in order to harvest this ATP. So here we see something organic. And look, yielding something inorganic, an inorganic form of carbon, but also all this energy. Now, if we were to look at the opposite reaction, you can basically just do this. But what I'll do is I'll just write it out anyways. So I'm going to write out the mirror image of this reaction. So we'll write out 6CO2 plus 6H2O. The big arrow here is going to yield the glucose plus 6 oxygens. Okay, so this is going to be a mirror image of the reaction at the top. The only thing different is when we broke down glucose, we yielded energy, right? Where would energy go with this reaction? Because now we're forming this organic carbon molecule. So would we be giving off energy, yielding energy, or would energy have to go into this system?
Into.
It'd have to go into this system. So energy goes in, and energy with this reaction comes from this big bright yellow thing that I hopefully, we get to see today. It's not out there right now, but this big yellow thing, of course, looking at the sun, so solar energy. So energy goes into this system, takes something inorganic, and create this organic glucose. What is the name of this reaction? Yep, photosynthesis. Okay, so this is photosynthesis. So basically aerobic respiration, photosynthesis, they are complete opposite reactions of each other. Absolutely know that relationship between the two. Okay, they're opposites of each other. Once you know how to write one out, you can write out the other one because it's just going to be, that mirror image. Okay, opposite. And this I'll say photosynthesis is what goes in that direction, backwards. So autotrophs, we're looking at taking this inorganic form of carbon and they can convert it into something organic. Okay, so autotroph meaning they can do that on their own. Autotroph, self-feeders. So not too bad for carbon, right? It's, something organic, heterotroph. It's inorganic, which would be CO2, autotroph. Okay, so not too bad for carbon source. Next up, we need to talk about energy source. Two categories for energy source. Energy source can get a little bit confusing, as we'll see coming up. But bottom line, we have chemo versus photo. Chemotrophs, they obtain their energy from chemicals. Not bad. Chemo refers to chemical. All right, what about phototrophs? Photo refers to lights, so here you're looking at photosynthesis. So energy is from photosynthesis. Not bad until you combine the term phototroph with the term autotroph, or the term phototroph with the term heterotroph. And then it comes down to, did the auto mean carbon or energy? Does the photo refer to carbon or energy? Which is why, in this case, flashcards might help keep these terms straight. So when we combine them, nifty little table in your book, table 7.3, okay, combines these terms, lets you know a little bit about them, which organisms fall into that category. I circled chemoautotrophs for a reason. There are 2 subcategories. Okay, they're put into 2 categories and they're not on this table. Okay, so I just want you to make special note of that, which is why I highlighted chemoautotroph. And I'll show you those categories in just a moment. All right, so let's start this portion of the lecture. So I try to color code it as much as possible, just to kind of have some things pop. So photo, again, refers to energy source. Photo refers to light. So they derive their energy from sunlight. Auto, it's in pink, can't really tell with the screen in here, but auto, okay, in carbon, auto refers to the carbon source, which would be inorganic, which is CO2. Okay, so you can look at photoautotroph, and something I might ask you on the test would be, all right, what is the carbon source? What is the energy source for a photoautotroph? You just need to be able to break that term down. Photo means light, that is energy. Auto means self-feeders, that is CO2 for carbon. Okay, so these organisms undergo photosynthesis. Here's the reaction in words. You just need to know the reaction. You can't remember, the formula for it, how I wrote on the board, or in words. It doesn't matter as long as you know that reaction. Here we can see algae, plants, some bacteria fall into this category. I mean, definitely plants, definitely, the photosynthetic algae, of course. Okay, so you're looking at these photosynthetic organisms producing oxygen from that photosynthesis. Next up, this is the most confusing category we have. Okay, so chemoautotrophs. Chemo refers to chemicals, so their energy source is going to be chemicals. Auto, again, refers to carbon source. Carbon source is inorganic with auto. Okay, so CO2. Now here's the situation with chemoautotrophs. What kind of chemical is it? Is the chemical organic or is the chemical inorganic? Depending on the type of chemical, that's how we have 2 categories. Category number 1, look at the name of it. Chemoorganic autotroph. It's a mouthful. I mean, it's a really big name, but try not to panic over it because it tells you everything you need to know. Chemoorganic, okay, organic chemicals for energy, autotroph, inorganic carbon for the carbon source. It's all right in the name. As long as you know which is energy, which is carbon, you're good. Okay, so that's a chemoorganic autotroph. It would be really, really nice, okay, in the world of microbiology, if the ones that used inorganic chemicals were named chemo-inorganic autotrophs, but we're not that lucky, okay, unfortunately. Instead, there's a brand new term, which is called lithoautotrophs. Basically, if you hear the term litho, you just have to remember inorganic chemicals. It's an autotroph, inorganic carbon. Basically, lithoautotroph, everything is inorganic. Inorganic chemicals, inorganic photocarbon, which again, you need to remember is CO2. Okay, so it relies totally 100%, as you can see, on inorganics. I put an example up here. And again, Prezi doesn't let me use subscripts, so it's a little bit annoying from a chemistry standpoint to look at this reaction and be like, the 2 should be small, the 2 should be small, the 4 should be small, this little 2 should be small, but kind of have to look past that, with Prezi. But basically, hydrogen gas, that's going to be their energy source. Carbon dioxide, there's their carbon source. They produce methane gas from that and some water. Okay, so it's a really good example of using all inorganic molecules. for both carbon and then for energy. Okay, so that's an example of a lithoautotroph. Methanogens, because they generate methane gas. Okay, 2 more categories. Photoheterotroph, I don't have much to say about them. You just have to be able to break the terms down. Photo refers to light, so it's going to be a form of photosynthesis. It's just a little bit different than your standard photosynthesis. It's a non-oxygen type of photosynthesis. Not really important. I just want you to know that their energy source is from the sun. Heterotroph, their carbon source is organic. This is what I want you to know. Okay. Special organisms in this category, not a very popular category whatsoever for organisms. Purple and green photosynthetic bacteria, they used to think they were algae. Then they saw that they had bacterial properties, so they renamed them pretty recently and put them into, assigned them as bacteria. All right, and then finally, last category we have, chemoheterotrophs. Chemoheterotrophs, everything is organic. Okay. There's no inorganic chemicals which are needed, so there's not like 2 categories how there are with, chemoautotrophs. Chemoheterotrophs, everything is organic. This is the category that you and I fall into. So we fall into this category, everything we require is organic. Energy, as far as, and also carbon. Just about all bacteria fall into this category. This is by far the most popular category we're looking at with these bacterial organisms. And here we see aerobic respiration, okay, which we already wrote on the board. Okay, so your glucose and your oxygen is going to yield your carbon dioxide, your water, and then of course your ATP. So again, if you're given on the exam the term chemoheterotroph, you need to tell me what the energy source is, what the carbon source is. And that goes for each group we just mentioned. And then a little review, looking at a couple other categories that exist for some of these chemoheterotrophs. One category would be the saprobes. Remember we talked about saprobes in an earlier chapter. They feed off of dead or decaying material. Leaf litter, so leaves that have fallen to the ground, they'll feed off of that. Trees that have fallen, animals that are no longer living, and so on. So mostly obligate, meaning that is the way that they feed. They feed off of something dead. They're no longer alive. Parasites, again, by definition, the term parasite, they feed off of a living host. So they feed off of that living host, and the host, gets harmed in the process. That's what we're looking at. So typically causing disease, of course, as they would be pathogenic. Syphilis spirochete, awesome example. Okay, so past person to person. Okay, and this is going to fall into that parasite, attacking the host, benefiting from the host. And once again, here's that table, okay, that shows each of the categories we talked about. And again, chemoautotroph, remember we can have chemoorganic autotroph and a lithoautotroph. There are the 2 categories within this one. Otherwise, everything else we talked about is up here. It's a really good table to study from. Also on page 177 in your text, it gives you a little bit of information. If you had med term, this will be very familiar, but it lets you know like what troph means, for example, or what hetero means. So it lets you know some of the terminology behind these words. Okay, so that may help you when you are studying. So check that out. Okay, so next little bit, we're going to do all of it on the board. Okay, so the rest of this chapter, in the next, I would say probably 20 minutes or so, we'll just do all this up here. Just like having you guys ready. Okay, So first thing that I would like to talk about, we need to talk about passive transport and active transport, but before we do that, let's just do a little review. As far as the cell membrane is concerned, what is the structure of the cell membrane? What was it? Phospholipid bilayer. Okay, so structure. Okay, so phospholipid bilayer. So again, we have these phosphate heads, these fatty acid tails. You can have these big, let's say, protein molecules embedded in the membrane. Okay, so that's your standard phospholipid bilayer. Do we have a cell membrane that looks like this? Yes. Do bacteria have a cell membrane that looks like this? Yes, they do. What is the function of this cell membrane? Yes, exactly. So transport. So letting things in or out. So we'll say import, export, letting things into the cell, letting things out of the cell. Keeping things out of the cell you don't want in the cell, and keeping things in the cell that you want to keep in the cell. Okay, so it regulates transport. Okay, the cell wall. What is the structure of the bacterial cell wall? Just think, the difference between gram-positive and gram-negative, what is that structural component of that cell wall?
PG.
The PG layer and the PG, peptidoglycan. So peptidoglycan. So I'll put in parentheses too, PG layer. Peptidoglycan, you see for the cell wall structure. Do we have a cell wall? Absolutely not. We do not. So bacterial cell wall composed of peptidoglycan. What does it do? What is its function?
Protection.
Protection. One function would be, I'll put shape, structure. That's not the primary function. Primary function is going to be what Anna said, and protection. Specifically, a lot of protection when the organism enters into an osmotic change in their environment. Okay, so we'll say protection from osmotic changes. Definitely be familiar with the difference between gram-positive, or I'm sorry, with cell wall and cell membrane. Okay. So what we'll talk about is passive transport, and when we look at passive transport, we'll talk about the difference between passive transport and active transport, but looking at passive transport, I'll start off by drawing a chart up here. And have a little slope like this. Way up here at the top, let's say there's high concentration of materials. Way down here at the bottom, much lower concentration. So concentration decreases as you move down. And time just progresses this way. It's fine. What's going to happen with passive transport is material moves this way. Okay, so it's going to progress from an area of high concentration down to an area of low concentration. So basically, molecules move from an area of high concentration to an area of low concentration. In other words, you can say that molecules move down or along what we would call the concentration gradient. Okay, so move down that gradient or along that gradient. Now, you're not looking at resistance, going along this gradient. So let's say Barbara was hanging out on her bicycle, right? And she's hanging out at the top of this hill. And she decides to, ride on down that hill on her bicycle. How much energy is she going to spend riding down that hill? Pretty easy, right? Just hold on, just fall off, that's about it. Okay, so you're looking at no ATP is required, which is why it's called passive. Okay, it's an easy type of transport. No ATP is needed. No energy is put into the system. Examples? First one we have is simple diffusion. Any class that you learn diffusion in and you're reading through the chapter, it's the same in this textbook. You're always going to see the characteristic coffee cup with a sugar cube in it example. It's like in every single science book when you learn about simple diffusion, because it's just illustrating that when you drop that sugar cube in, you have all those sugar molecules compacted in this little tiny cube. You drop it in and those little molecules are going to bombard and kind of hit each other and spread out from an area of high concentration and disperse to areas of low concentration. Okay, kind of have that equal dispersion, throughout. So that's what simple diffusion is. So you're going to have, we'll say molecules move on their own across the membrane. So we're talking about the cell membrane here, transport in or out. Okay, so they move on their own. We'll say no protein carrier needed. These are like nonpolar molecules that can easily move across. You're not looking at anything with a charge. There's a charge, like an ion, it's going to have a hard time moving across. So that's what simple diffusion is. We also have facilitated diffusion as another example. So let's just say this was example 1, facilitated diffusion example 2. With facilitate, what does the word facilitate even mean? Help. To help. Okay, so helping out. So with facilitated diffusion, you still have diffusion across the membrane. However, you have something to help. So we have a protein channel or carrier to help transport these molecules across the membrane. Okay, so there's something there to help them get across. This is good for larger molecules or ions, for example, calcium with that 2+ charge, a calcium ion has a calcium ion channel to help it get across the membrane. With all of this, we're talking passive transport, so those calcium ions move. They're either going to go out of the cell or out to into the cell, depending on concentration. Remember, they always go from where there's a lot of them to where there's less of them, always, just to balance it out. With facilitated diffusion, there's a few properties we need to keep in mind. So with these properties, we have something known as, just write it over here. specificity. That means there's a calcium ion channel, calcium ions go through. There's a chloride ion channel, chloride ions go through. Nothing else can get through, so it's very, very specific. We also have something referred to as saturation. That means the more binding sites on the protein, then the more molecules can move across. So it's faster. Okay, so it'll be faster the more you have. It'd be like, for example, if we had to move all these chairs into the hallway and I was the only person in this room. Okay, it's gonna take me a long time to get every single chair out. But then if I had you guys help me, we each grab 1 or 2 chairs, we can get all the chairs out in a minute or 2. Okay, so we have more binding sites, we have more molecules, we can get across faster. Last thing about facilitated diffusion, there may or may not be some competition. So that means if something very similar may be able to bind and get across that membrane, and this is similar to, this is actually exactly what we talked about. Competitive inhibition, the example we used, antibiotics in class last week. Okay, so competitive inhibition, if you have an inhibitor that's similar, has the same shape, could potentially get across. Okay, so that's how a lot of antibiotics are brought into the bacterial cells. Okay, again, mimicking the typical substance that binds to these proteins. All right, and then the last type of passive transport we'll talk about is the biggest topic, which is going to be osmosis. Okay, so number 3, and let's put this over here. Movement of water. Osmosis, you are looking at the movement of water across the membrane. Okay, no protein is needed to carry this water across the membrane. Okay, so we're just looking at the movement of water. With osmosis, we are implying that the solutes, okay, those substances like salt or sugar, cannot go across the membrane. The only thing that can to achieve equilibrium is water. Water goes from the side that has a lot of water to the side that has less water. Or you can look at it that water is going to go from the more diluted side to the side that has the higher solute. Okay, it's going to be almost attracted to the saltier side. Okay, so let's go through. We have 3 categories that we need to take a look at with osmosis. First one, actually, make this a little lower so I'll put some notes on the top. We have an isotonic solution. So isotonic solution. Let me just sum something up first. Solute would be the substance that gets dissolved, such as salt. Okay, such as salt. A solvent with any solution is what does the dissolving. So that would be the water in these scenarios, and then solution would be the 2 together, salt, water. Okay. So if we look at an isotonic solution, we're gonna have, you know, the salt and the water present. Let's look at this, draw a schematic. You know, in an anatomy class, you'll have the same thing going on, and the most common example would be, you know, red blood cells, okay, sitting in an isotonic solution or hypotonic hyper. We're not in anatomy, we're in microbiology, so we're gonna draw a bacterial cell. Okay, and the process will be very similar, slightly different, but very similar. Here's your bacterial cell, isotonic solution. Tonicity refers to concentration. Iso means same. So we're gonna have the same concentration inside the cell as we do outside the cell. So if we have 10% salt outside the cell, we would have 10% salt inside the cell. It's isotonic. So if we have 10% salt outside, we can say we have 90% water outside, so 90% water inside. Two questions. One question, where does water go? It's gonna go towards the salt, but in this situation, it's all equal. Does water get attracted inside the cell, or does it wanna move out of the cell? What does it do?
Yes.
It just kind of hangs out. You might have a little bit of water leave the cell, but then a little more comes in immediately. So basically, you have this going on. Okay, so I'll say H2O exits, enters cell, we'll say equally. And then parentheses, I'll say no net diffusion of water. That means it doesn't, you know, leave the cell any more than, you know, more comes in. It's gonna be equal. Water's never 100% stationary. A little bit comes out, a little bit comes in, great. But it's gonna be overall no net, you know, diffusion. Either way, what happens to the cell in this scenario? Does it swell up? Does it shrink? No, it's fine. So cell stays the same. If you were a bacterial cell, would you like this environment? Bless you. Yeah, it's a pretty good environment. Okay, really nothing's happening to you in this environment. It's not the best environment for bacteria, believe it or not, but it's a second best. It's pretty good. Next one we'll look at is hypo. Okay, hypotonic solution. What does hypo mean?
Low. Oh.
Low, below. So here, you draw this one out. Well, what has the lower concentration? The solution out here or the bacterial cell?
Solution.
Yes. When we talk about these, we're talking about the solution out here. So if we were to do this, let's do 10% salt outside the cell. So hypotonic, would I put 5% salt in the cell or maybe 30% salt in the cell?
30.
30, because you want higher. So in this situation, which way would water move?
Cell.
It's gonna move inside the cell. So up here, I will say water moves hypo to hyper, meaning it goes from the hypotonic side to the hypertonic side. You can also say water You can also say water moves down its own gradient in the sense that we already said water is going to move into the cell, right? Because it's going from hypo to hypertonic. All this salt's going to bring more water in. And you can look at it another way. You can say, well, there'd be 90% water out here, 70% water in here. So water's gonna go down that slope, or it's gonna go down that gradient. Lots of water to less water, so water's gonna come in just to equalize everything. So water moves in. So we'll say H2O moves into the cell. What's going to happen to that cell?
Burst.
Bursting, now as far as a cell bursting, if we were back in, anatomy, yes, that you would be looking at that. With bacteria, it's a little bit different because what do bacteria have that we don't have that protects them against changes? They have the cell wall. That's going to provide a lot of protection in situations like this. Is it, the end all where, they're not going to be untouched whatsoever? No, because if their cell wall starts to break down, then yeah, this is going to be a very bad situation. But their cell wall is going to help to protect them. So we could say the bacterial cell swells. Later on, it may, and of course depending on the severity of the situation, it may burst, but cell wall helps to protect it. Okay, cell wall helps to protect it. Okay, this situation that we just drew, so this water rushing into the cell, do you think this would be a good situation for bacteria or a very poor situation for bacteria? It's going to be better or worse than isotonic. I think it's a better scenario or a worse scenario? It's actually better. This is the best scenario if you were bacteria. Let's just say. Best little scenario right here. Actually let me back up. Do bacteria have mitochondria or any membrane-bound organelles? They don't. Where do they do a lot of their metabolism?
The cytoplasm.
In the cytoplasm. What is the cytoplasm mostly made up of? Water. They need a healthy influx of water coming into their cells. So they have this water, they can undergo their reactions, do all these metabolic processes in the cytoplasm. This is a really good situation for bacteria. Okay, it keeps that water coming in. Okay, so good situation for them. Last one we have hypertonic solution the bacteria is hanging out in. So if we look at this situation, what does hyper mean? Above. So here's your bacteria. So then looking at the solution, let's put 30% salt out here. Let's put 10% salt inside. What's going to happen to water?
It's going to move into the solution.
It's going to move into the solution that the bacteria is sitting in. So water is going to move out. This is a pretty bad situation for bacteria. Again, they want to keep that water so they can undergo their metabolism. Here they're losing a lot of this moisture. They're going to become dehydrated. Another way to look at it, again, 90% water inside, 70% water outside. Water's going to go down its gradient. That's why it's called, passive diffusion. So what's going to happen? We'll say H2O moves out of the cell. The cell can shrivel up a little bit. Okay, become dehydrated. Not a good situation. Because you're taking water, or taking that water away from the bacteria. It's going towards the saltier side. Okay, so that's a look at osmosis. Any questions with that? All right, so last thing I have, and then we'll take a little break, just a couple minutes, is looking at active transport. We don't have as much to look at with active. We do look at active. Let's draw the same slope. Okay, so this is concentration, high concentration at the top, low concentration at the bottom. We're gonna move backwards this time. We're gonna go this way. Probably should have drawn the slope in the other direction, but regardless, we're gonna go up the hill this time. So with active transport, we are gonna move from an area of low concentration to an area of high concentration, going up that slope. You can also say you are going up or against. Up or against the concentration gradient. Going up that hill, we're going against the grain, so to speak. Okay, we're going the opposite direction. So let's put Carly on a bicycle, and we'll put her at the bottom of the hill, and she needs to ride to the top of the hill. Is she gonna spend some energy doing that? Yep, and depending how steep this is, how big the gradient is, you may need more energy for that. So we'll say ATP. Let's say ATP input is required. Okay, so you need ATP to do these processes because you're going backwards. You're going from low concentration to high. So some energy needs to be present to overcome that. A couple scenarios. One of them would be, so let's just say examples. Permeases. A permease is a protein pump, not to be confused with a protein carrier, a protein channel. The word permease is just a fancy term for protein pump. If you hear pump, active transport. If you hear channel or carrier, passive transport. Just be clear with that terminology. Pumps work by pumping against the gradient, always. Carriers, channels, go with the gradient. Classic example. Sodium potassium pump. Okay, classic example, active transport mechanism. From low to high concentration. Other example we have is endocytosis. This would refer to bringing materials in, but the materials do not pass through the membrane. They don't physically go through the membrane. My hand is the membrane. With diffusion, osmosis, the water, whatever it may be, moves through the membrane just like that. Just like that marker passed through my fingers, through my hand. With endocytosis, it's almost as if the membrane of the cell is going to act as pseudopods. It almost comes out, reaches around, forms like a bubble, which is referred to as a vacuole, and brings the material in. But it never physically passes through the membrane like that. Two types of endocytosis. One is called phago. Cytosis, where you bring in large solid molecules, like a whole bacterial cell. The other one is pino. Pinocytosis is bringing in liquids. Phagocytosis is almost like cellular eating because you're bringing in solid material. Pinocytosis is like cellular drinking because you're bringing in liquids. Yeah, but they do not cross that, do not pass through that membrane. Questions? Okay, I'm going to drop the screen back down. We've got a quick concept check. check to take a look at. I'll just kind of pass through a few images up on the Prezi and then that concept check. Okay, so again, passive transport on here, you're gonna see all of the processes we talked about. So the order I have it on here is osmosis. So again, osmosis is water is gonna be the only thing that moves across that membrane. It physically goes across that membrane. It goes from where there's low solute to where there's high solute. So water gain is gonna be on this side. Volume increases, so that's why the cell would swell when water rushes in. There's an image in your text that looks like this. It shows all three scenarios that we did on the board. Okay, so you can read up a little bit more about it, see what takes place in which situation. You know, the cell would swell versus shrivel. Okay, so hypo versus hypertonic. Simple diffusion, your text has that characteristic sugar cube in coffee scenario. Okay, so looking at, not spending any energy, of course, because it's passive transport, non-polar molecules, lipid soluble, anything that can pass through that phospholipid bilayer very easily can get through. The steeper the gradient, the faster the molecules get across. It's just like Barbara riding down that hill. The steeper it is, the faster she's going to move down that hill. Facilitated diffusion. Again, no energy. You go from an area of high to low concentration, and there's some type of a protein carrier or channel to help move molecules across. These are the three properties we discussed. They are specific. There's a saturation, meaning a certain number of binding sites to help aid molecules across. More binding sites you have, faster molecules move across. I use the analogy of the chairs. You're taking the chairs out of the room, more people, faster it goes. Competition, again, antibiotics designed to mimic a number of molecules that can move across these carriers. So something with a similar shape can bind and possibly get through. Little image in your text, so table 7.4 shows an example of simple diffusion versus facilitated diffusion. Facilitated, again, has that carrier, has that protein in the membrane, high concentration to low concentration until you hit that equilibrium. Active transport, this is where we require an input of ATP and we go against the gradient, up the gradient. Okay, which is why it's called active transport, because it requires that input of energy. Permeases, those protein pumps. One example of active transport, sodium-potassium pump, good example. Endocytosis is when we're bringing in a lot of material, large material. It doesn't technically pass through the membrane, not transported through it. The membrane almost kind of goes out and grabs it, utilizing a pseudopod type of movement. Okay, phagocytosis again versus pinocytosis, bringing in solids, pino is bringing in liquids. Little schematic here, this one I'll zoom in on. So this is table 7.4, continued. We can see active transport with the permease here, going from an area of low concentration to high. So you're going against the grain, you're going up the gradient, against the gradient, requires energy to do this. Down here at endocytosis, phagocytosis, you're bringing in solid molecules, and you can see the cell membrane almost goes out, wraps around it, and brings it in through this bubble-like vacuole. Okay, so these purple guys, the little bacterial cells, don't technically pass across the membrane like we saw with, utilizing a pump or with simple diffusion. And then pinocytosis, you're just looking at liquid kind of being pinched off in a similar manner and brought in via a vessel. Okay, and these would require energy. Bulk transport, you're bringing in these large molecules, that's going to require some energy from the cell. Here you can see an oil droplet easily moving across, lipid.